So we can look at covalent bond strength, and bond strength is a measure of how much energy is required to break a bond. So bond strength is listed as the energy required to break a bond, so it's always a positive value. It's called bond enthalpy because it always takes energy to break a bond. So if I look it up on the table, and I think I'd given you a table earlier, 242 kilojoules to break this bond. Always positive. Always requires energy to break a bond. Okay? So energy must always be added to break a bond. Okay? All these values, therefore, are positive. And what you will see if you compare is a C bond. Let me see. I know this one here is 348 kilojoules. Double bond, 614. Triple bond, even more. So higher electron density in here causes the bond to be much stronger, pulling this closer together, like 3 bungee cords instead of 2. So multiple bonds are stronger bonds. Now if you look at enthalpies of a reaction, and again P in this reaction, you can look at bonds broken minus bonds formed. Now, this gets a little confusing because it's always products minus reactants when we did the change in enthalpy before. What you need to know is bond breaking always is positive energy, and bonds being formed is always a negative energy. Okay? So in order for this reaction to occur, I need to break the bonds between the Cl and the Cl, and the C and the H. And that is endothermic, requires a bunch of energy. But when these come back together, okay, these bonds are formed, that releases energy. And if the net is a greater release, then this is going to be exothermic, right? But bond breaking, first step, always requires energy. Bond formation always releases energy. And you don't know whether it's exothermic or endothermic depending on the difference in the height and where these end up. Okay, but you do know bonds broken, positive, bonds formed is negative, and the net tells you what the change in enthalpy is. Okay? So this is how we'd go about calculating the bond enthalpy for a reaction, or the enthalpy for a reaction using bond energies. So here we have our reactants and our products. So in order for this reaction to occur, I have to break these bonds and form these bonds. So in order to figure out the energy, you really have to draw the Lewis structure. So if I have CH4, this is what I have, and I have Cl2, and I'm just looking at the bonds, I'm not too worried about the lone pairs, and I'm making CH3 Cl plus HCl. So what I have to recognize is that I have 4 CH bonds, 4 CH bonds that have to be broken. I have 1 Cl bond that has to be broken. And I'm going to take that energy and subtract from it the energy that gets released when I form bonds. So I'm going to make 3 CH bonds, as indicated by these 3, plus 1 CCl bond, this one here, plus 1 HCl bond. And I'm going to use the bond energies in that table that you have in your packet. So the way this would work is, here's what I've written, is the change in bond energy for CH times 4 plus the change, this is energy in, and what I get out is the energy from forming these bonds. Okay, so I just plug in the values from the table. And when I do that, this is what I get, and I get a final value of negative 104 kilojoules, which means it's an exothermic reaction generating 104 kilojoules of energy. Okay, So try this one. Okay, welcome back. So I need to look at, I'm breaking one of those and one of these. That's going to be my positive energy. And what I get out is 2 HFs. That's energy released. So here's the equation for that. I plug in the numbers. And again, what I get is an exothermic reaction. Okay, the other thing I can look at besides bond enthalpy or bond strength is bond length, because the length of the bond is an indication of how strong it is. The shorter the bond, the stronger the bond. And what you'll notice here is that triple bonds are shorter and therefore stronger than double bonds. So if I look at just the 3 carbon bonds, the single bond is 1.54 angstroms, 1.34 angstroms for a double, and 1.2 angstroms for a triple. Okay, and you can see that throughout. And the smaller the atom, the smaller the bond. So because nitrogen is a smaller atom than carbon, single bond for each, I'm going to have a smaller bond length for the nitrogen-nitrogen bond. So we can also measure an average bond length for different types. As the number of bonds between the atom increases as I go from single to double to triple, the bond length shortens. Another term that sometimes gets used is if I have a single order, I can talk about its bond order. It's pretty simple here. Single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. So try to answer this question. What is the bond order of the bonds in ozone? Okay, welcome back. As it turns out, the bond order is 1.5 because I have a bond order of 2 here and a bond order of 1 here. And remember, these are averages of the two, so I end up with a bond average of 1.5.
And so if we have two atoms, they're both going to be attracted to one another. And where does that attraction come from? It's the electrons of one atom being attracted to the protons of another. And so that's going to pull atoms together. But if they get too close to one another, then there's going to be repulsion. And we can measure these forces just using an energy distance graph, where we've got the energy that's pulling those or pushing those apart, and then how far they are physically separated. And using a graph like that, we're able to determine the bond energy, the energy holding them together, and also measure the bond length, how far those atoms are going to be apart. And so the bond energy, if we were to define it, is simply the energy required to break those atoms apart. Now likewise, when we form a bond between the two, we're going to release energy, and that's just simply the negative bond energy. Now the strength of that bond, or the bond strength, is going to be built upon the charges of the atoms themselves. The bigger the charges are, the greater that bond energy is going to be. And as we increase the number of electrons in a bond, so as we move from a single to a double to a triple bond, we're actually increasing the charges and therefore increasing that bond strength. And one interesting thing that you should know is that as we increase that strength, we're going to pull those atoms together and we're going to actually decrease the bond length. And so if we look at these two representative atoms right here, as we bring them close together, there's going to be attraction. In other words, as we shorten the distance between the atoms, as they get closer and closer together, there's going to be a greater attractive force. Now, as they start to get really close together, there's actually going to be repulsion between those two atoms that's going to push them apart. And so we can find what's called that Goldilocks, the point where they're not too close, not too far away, and we're going to have the highest amount of energy right here. And they're just going to kind of vibrate at that space. So if we were to look at two atoms, like two atoms of hydrogen, we would find that that energy to distance graph would look something like this. There's going to be attractive force between these two hydrogen atoms out here, but as we bring them closer and closer together, that energy of attraction is going to get greater. As we move them even closer, then we're going to move into this whole idea of repulsion. And so this is going to be that Goldilocks area right here. And so what we can measure then is the bond energy, the energy holding those atoms together. And likewise, since we've got distance here on the x-axis, we can measure the bond length, how far those atoms are apart. And so if we defined what is bond energy, it's just two atoms connected together. And so bond energy is the energy absorbed when we break those atoms apart. Now likewise, there's going to be energy that's released as we bond those together, and that's going to be the negative bond energy. It's going to be exactly the same. The amount of energy to break it apart is the same amount of energy that we get when those two atoms are going to be attracted together. Now what contributes to that bond energy? It's going to be the electronegativity of all the atoms involved in that molecule. And so let's say we were to look at boron. Boron is going to have an atomic radius of 83 picometers. What does that mean? The distance from the center of that nucleus to the outside is going to be 83 picometers. And so if we were to connect a boron to a boron, we would anticipate that that bond length, the distance between the two atoms, is going to be twice that. It's going to be 166 picometers. But if we were to measure the actual bond length in a molecule, let's throw one up here, and it ends up being 175 picometers. In other words, they're farther apart than we would expect. That means that we're going to have a very weak bond between these two atoms. And so basically, as we increase that bond length, that distance between the atoms, we're decreasing the bond strength. Now if we were to use another example, let's say we're looking at rhenium, which has a radius of 137.5. If we had two rhenium atoms, we would expect that that bond length is going to be 275 picometers. If we actually measure it in a molecule like this, and it's less than that, that means that they're really overlapping. There's greater charges holding it together, and so we would call that a strong bond. Again, the higher your bond energy is, the closer those atoms are going to be, and the shorter that bond length is going to be. Now what happens as we increase the bond number? Let's say we're looking at two molecules that look essentially the same. We've got ethane, which is carbon attached to carbon and then hydrogen around the outside, and then acetylene. And so this is the same thing, carbon attached to carbon with hydrogen around the outside, but in this case we've got a triple bond right here. How is that going to affect the bond strength and the bond length? And so if we look at these two carbons, we've got one that's a single bond and one that's a triple bond. If we were to measure their bond length, we would find that as we increase the number of bonds, we're actually decreasing that bond length. They're getting closer and closer together. Well, what does that tell us about the bond energy? The bond energy is increasing over time. So again, the more electrons that we're sharing, the more charges there are, the greater that bond energy, and therefore the shorter the bond length is. If we were to measure the same thing with nitrogen, single, double, triple bond, we'd find that we're decreasing the bond length again. So what's going to happen to our bond energy over here? It's going to increase over time. And so did you learn to describe the energies involved in both breaking and forming chemical bonds? I hope so, and I hope that was helpful.